atomic orbitals and electronic configurations. So basically, we have studied that the atoms are such type of models in which the electrons are revolving around their nucleus in some specified orbits or called as shells, and then protons and neutrons are present inside the nucleus. Now, our basic purpose in this chapter is to have some further details on the orbits or shells of the atoms and how they are classified into further subcategories of orbitals and subshells, and then we will also see their shapes, their names, then capacity of holding the electrons, and then we will see some electronic configuration. How do we represent the electrons present in the atom in the form of the electronic configuration? That's our target in this topic. So quantum shell, as the name indicates, that these are the shells which have some specified energy associated with them. Quantum comes from the word quanta, and quanta means packets of energy. So quantum shells means the shells having their specified energies or defined energy levels. So we can call shells as energy levels or quantum shells. Clear?
Yeah.
Now, the structure of the atom is basically with this chart, and that's I remember. We studied the structure of the sodium model, and I showed you why these values are shown at different energy levels. Can you tell me what these two values represent if we consider that that's the structure of the sodium, to which these two electrons belong to?
First shell, inner shell.
Yes, the first and inner shell, and this last electron represent the
Third shell.
very good third shell, and that's the first shell. And these these 8 electrons represent the second shell. Very good. Now let's move ahead. So why the ionization energies increase in magnitude? Like why their values are getting higher and higher as we keep removing the electrons? Basically, when we remove some of the electrons, then the positive charge on the atom keep increasing. Let's suppose if we have again sodium with atomic number 11, and it has 8 electrons in it, it has 11 electrons in all of 3 shells combined, but when we remove 1 electron from the total electrons, we will get 10 electrons, but the protons will remain the same. They will not change. We'll have 11 positive charge on the 11 protons and 10 negative charge on 10 electrons. So as a result of this, the positive effect or the nuclear charge effect on the remaining electrons will be higher, and as a result the attraction between the remaining electrons of the atom will have higher attraction with the already present 11 protons in the nucleus, and as a result of this you will need to give more high ionization energy to remove the remaining electron. Is it clear?
Yeah.
So the ionization energy is basically the energy of the electron when removed minus energy of the electron when in the orbital. So basically there's energy of the electron when it is removed, and the other energy is of the orbital. Anyways, leave this, but what I told you that it should be increasing because of the increasing positive nuclear charge. So why do the successive ionization energies of the sodium increase? It is the same reason. As we keep removing the electrons, we are basically increasing the positive effect of the nucleus on the remaining electrons. Moreover, there is a sharp jump in the ionization energy is when we are removing the electrons from a complete shell. Let's suppose we have sodium. Sodium has three shells. So when one shell is removed, let's suppose there are three shells in the sodium. When we remove one shell, then the next electron will be closer to the sodium nucleus, and as a result of this there will be stronger attraction between the electrons of the second shell and the nucleus. So that's why the ionization energy increase. Is it clear?
Yeah.
All right. There are some tips on this. Remember that electron repulsion exists between two electrons that are in the same orbital. So can you name any of the orbitals of p subshell?
One P1. Can you repeat the question?
Can you name me orbitals of the p subshell?
P1,
p1,
P2.
totally wrong, Ali. You are not doing the revision. It's px, py, and pz. Okay? Do you remember these names now?
Yeah, I don't know where to memorize the names. I know.
There are just three orbitals and you should have these names in your mind. So these are the orbitals of the p subshell. Now they are saying when there are two electrons in the same orbital, then as a result there is a kind of repulsion between them. So let's suppose we consider px orbital, and when we have a pairing of the electron, then there is a repulsion between them. So this leads to a decreased ionization energy. When there is a repulsion between the electron, there will be less ionization energy between them. Now there is also a repulsion of the electrons when they are present in the same shell. If this is a shell and we have, let's suppose, 5 electrons in the same shell, then there is also a repulsion between these electrons. So the electrons are also showing repulsion between them within the same shell. Alright?
Yeah.
And this point states that the repulsion is most significant between electrons in adjacent quantum shells. So again, if there are 3 quantum shells in the atom, then the repulsion will be most significant between shell number 1 and 2nd, or 2nd and 3rd. 1 with 2nd and 2nd with 3rd. So the repulsion will be significant between these combinations. Alright?
Yeah.
And moreover, the electron repulsion is also called shielding or screening. What is this shielding or screening?
Same thing as electron. What is actually?
What's this?
The repulsion between the electrons in different shells.
No, repulsion between the electrons, not the screening. Basically, the screening is actually the reduction in the force of attraction. Reduction of force of attraction between the valence electrons and the nucleus. That's the screening effect. That's the shielding effect. When we have less attraction between the valence electron and the nucleus, that is called shielding or screening. And why it happens? It happens because of the repulsion between the electrons. Are you getting my point?
Yeah.
Now let's suppose this is the structure of a simple atom in which we have electron in the first shell and then electrons in the second shell and then electrons in the third shell. So because of these electrons repulsion, the valence electron are moving away from the nucleus. All these electrons repulsion are playing their role uh, to repel the electrons of the valence shell away from the nucleus. And when this happens, the attraction between the valence electron and the nucleus decreases. This causes shielding or the screening. Is it clear?
Yeah.
All right. Now they are considering the electronic configuration of some of the atoms by taking into account the energies. The hydrogen has electronic configuration of 1s1 and helium has configuration of 1s2. So in this orbital of helium there is a greater repulsion between the electrons. So this repulsion is basically creating a greater energy between the electrons in the 1s2. If I draw like this, then there is a pair of electrons in this 1s orbital, and this repulsion between one electron and a second electron in the pair is basically creating a higher energy in the 1s. It is creating a higher energy in the 1s orbital. All right.
Yeah.
Okay. On the other hand, we also know that there is also an increased number of the protons in the helium, because helium atomic number is 2 and hydrogen atomic number is 1. So both the factors are taking place at the same time. The repulsion between the electron is increased, and on the other hand the nuclear charge or the attraction of the protons on these two electrons is also increased. So as a result of this, there is a greater attraction between the electrons and the protons. So we will consider that when we move from hydrogen to helium across a period, then the ionization energy will increase. Ionization energy increases when we move from left to right across a period. Is it clear?
Yeah.
Basically, there are two factors taking place. There is an increased nuclear charge and that there is an increased shielding. Shielding was because of the repulsion between the electronic pair in the helium. So this increased shielding is not that much dominant as compared to the increased nuclear charge of the helium. Helium had two protons in the nucleus and it has kind of repulsion between its electronic pair, but the increased nuclear charge had a dominant effect as compared to the increased shielding. So that's why the ionization energy is increasing from left to right. What is the effect of the increased nuclear charge on the ionization energy?
It increases.
Why it increases?
Effect is more than the effect of the shielding.
No, what has an effect of nuclear charge on the ionization energy? Just consider the effect of nuclear charge on the ionization energy.
there's more, the stronger pull from the protons because there's less electrons. So the positive force is stronger from the protons.
Positive forces of the protons stronger. So what they do with the electrons?
They have a stronger pull on the electrons.
Yes, they have
It's more,
stronger. Exactly, they have stronger pull on the electrons. So as a result, they become difficult to remove the electron, and higher energy is required to remove the electron. Right?
yeah.
Okay. Now after hydrogen to helium, we now move on to the next element. They are moving from left to right across a period. First, they took the uh, comparison of hydrogen with helium, and now they are considering the comparison between helium and lithium. So, what effect do you find here while moving from helium to lithium? What kind of change are you looking at?
Less first ionization energy
Why?
because there's one electron on the outer side.
And there is one more proton in the nucleus.
The effect of the electron shielding is stronger.
The effect of shielding is stronger because the one electron in the shell. Are there just one shells in both of these elements?
There's two in the first shell and one in the second shell.
In case of helium or lithium?
Lithium.
Lithium. So yes, you say that lithium has two shells now, and the second shell is more shielded. So that's why the ionization energy will be lesser as compared to helium. So yes, while moving from helium to lithium, now the lithium has three protons, or in other words, there are three plus charge, and helium has a 2 plus nuclear charge. But the electron to be removed from the lithium is from the second quantum shell. This second shell is present at a higher energy level. You have different ways to express this thing. Why ionization energy will be lesser? Because the electron is present in the second shell, which has a higher energy. You already know that as we keep moving away from the nucleus, then the energy keep increases. High energy shells have high energies, right?
Yeah.
And moreover, the electron present farther away from the nucleus will have less attraction with the nucleus. Moreover, there will be stronger repulsion between the electrons of the farther away electron. Like this electron will have greater experience of the repulsion from the inner link electrons of the first shell and the second shell. So all these factors in combined will give you a lesser first ionization energy. Now we can summarize these points. The factors that affect the energy of the electron are the orbital in which the electron is present. Orbital means it is present in p orbital or it's present in s orbital. So there's a reason, there's a factor. The second point is that the nuclear charge also affects the ionization energy. The nuclear charge means the number of the protons present in the nucleus, that affects the ionization energy. And then shielding. Shielding, as you have told me, it is a reduction in the force of attraction between the nucleus and the valence electron. So shielding also affects the ionization energy. Now they are going to tell us about the ionization energy trends across a period and down the group. Can you predict what shall be the trend across a period?
So,
While considering this periodic table, what do you expect? What shall be the trend of ionization energy across the period? Will it increase or decrease or what?
It will increase across the period and decrease down the group.
Yes, very good. So down the group it definitely decreases, and across the period there is a thing. Across the period it generally increases. Generally it increases, but specifically speaking there are some exceptions here. You have to consider some exceptions as well. Ionization energy does increase when we move from left to right, but it does not increase at certain points, and they have mentioned the exceptions. I hope it is mentioned here somewhere. I will tell you the so across a period, as we move from lithium to neon across period 2, the nuclear charge increases as the number of protons increases. This on its own would lead to an increased attraction between the nucleus and the electron, and therefore a decrease in the energy of the outermost electron and an increase in the first ionization energy. Decrease in the energy of the outermost electron, it means that the energy of the electron itself is decreasing. That it doesn't represent the ionization energy. It is not the ionization energy. It is showing the energy of the electron present in the outermost shell. Are you getting my point?
Yeah.
Whereas this
If
is
the
if
electron makes energy, we need more energy to take it out.
yes, this is the ionization energy. Ionization energy is inversely proportional to the energy of the electron. It is inversely proportional to energy of the electron. If electron has already a higher energy, then you will require less ionization energy, and vice versa. Clear?
Yeah.
And then we have but counteracting this, one more electron is added to the quantum shell on each occasion, and this increases the electron repulsion within the quantum shell. This on its own would cause an increase in energy of outermost electron and would lead to a decrease in the first ionization energy. So both the factors are being carried out here. When you move across the period from left to right, basically you are increasing the nuclear charge, and also you are creating the repulsion between the electrons within the same shell. So both these factors are happening when we move from left to right. But what is the summary? The increase in nuclear charge is more significant than increase in the electron repulsion. So this has a higher upper hand as compared to the other factor. Increase in nuclear charge has a higher upper hand, or it is more significant, it is more dominant than the electron repulsion. So that's why the first ionization energy increases across the period. Is it clear?
Yeah.
All right. This is happening in the same way in period 3, but you will need to exclude the D block elements. The D block elements means the transition elements, because for transition elements there is another type of the trend which we will discuss later on. Now while moving from down the group, the size of the atom is increasing, and as a result of this the shielding also increases. Shielding increases, the atomic size is increasing, the nuclear charge, what happens to the nuclear charge? Does it increase or decrease?
Across the
Down the group.
increases.
Yes, it increases. Good. Down the group it also increases. So basically all these factors increases while moving down the group. So this nuclear charge should show that the ionization energy must increase, but actually the ionization energy decreases down the group. it decreases while moving down the. Why is the reason?
There's more shielding, so the valence electrons have the most. As you go down, they have more electron repulsion. The electrons have less energy. So
Higher electrons have higher energy.
yes, yeah, they have higher energy, so less.
Ionization energy.
Yeah, less ionization energy required to.
Exactly, very good. So you will say that moving down the group, the number of shells are increasing, the repulsion between the electrons is increasing, and as a result, the electron repulsion increases, and the energy of the electron increases. Shielding also increases, so that's why ionization energy decreases. And if any question comes why the nuclear charge is not increasing the ionization energy down the group, then you will say that it has less effect or it is less significant as compared to the rest of the other factors of shielding, atomic size, electron repulsion. All right.
Yeah.
Okay, good. On this occasion, the combined effect of adding an extra shell and increasing the shielding is more significant than the increase in the nuclear charge. So that's the thing you will need to put in your answer. Extra shielding is more significant than the increase in the nuclear charge. So basically, this is the in group 2 from beryllium to barium, group 5 nitrogen bismuth. Basically they are considering periods number 2, period number 3, 4 and all the elements of the group 5 to 6, 7. They have included the period number 5, 6, 7 as well. In group 4, lead is anomaly does not fit in the others because it has a first ionization energy that is higher than that of tin, the element immediately above it. There is no general trend in first ionization in group 3 to thallium. The explanation for the anomaly group 3 and 4 are not included in this book, but they illustrate that in chemistry you can really apply a simple pattern or trend to all situations. So it is a fact that in chemistry you will find a lot of exceptions. Not a single trend can be applied anywhere. They will always lie some anomalies or some exceptions. So this exception is not going to be discussed here, so we will definitely leave this thing behind. Is it clear to this point?
Yeah.
Okay, now comes the groups, periods and blocks. You must be familiar with the groups and period. What this block is?
Group 1 and 2 transition metals. Not sure.
Not sure. Okay. Basically, here you need to apply the electronic configuration. Can you tell me the electronic configuration of any unknown element, but just you should know the order of the energy of orbitals? Can you tell me the order of energy of the orbitals? How do we write the electronic configuration?
It depends on the electron, but would be
All right.
S and then number of electrons, and then
just give me a general trend. Give me the general trend of the order.
1s, and then 1s2.
Okay.
2s2. 2p6. 3s2. 3 6. Then 4:2.
Very good. Hmm.
Then T10. And then 3D 10, 3D10.
Yes, good.
Yeah. Then 4P6.
Very good. Very good. So you should have this mind, like you did try to complete it by struggling, but you should have this clearly, fluently. Okay. After you already familiar with the electronic configuration, then this block means that whenever you write the electronic configuration of any particular element, let's suppose you are writing electronic configuration of sodium and it will end at the last subshell is 3s1. That's the last subshell. This last subshell is S, so it means the element will belong to S block. So basically the periodic table is divided into 4 blocks: S, P, D and F blocks, and these blocks are basically according to the electronic configuration of the atoms. The electronic configuration where it terminates at the last subshell, it will be the same block of that element. Is it clear?
Yeah.
So for all the elements which are present in group number 1, the electronic configuration will end at S1, and this N represents the period number or quantum shell number. It can be 1s1, 2s1, 3s1, but it will end or it will terminate at S1. So the block of this element will be S block. Clear?
Yeah.
Same goes for elements of the group 2. Their electronic configuration ends at S2. So this will also belong to S block. For group 3, the electronic configuration will end at P1. Let's suppose take an example of the boron. Boron is electronic configuration is 5. Electronic configuration will become 1s2, 2s2, 2p1. So it is considered in general form as ns2 np1, but the last subshell is p, so which means this element will belong to p block. And the next group 4, it also terminates at p subshell. Group 6 ends at p subshell 6, 7 and 8. So all the elements starting from group 3 to group number 6, all the elements ends at p subshell, so they all belong to the p block. Is it clear?
Yeah.
All right. So here they have mentioned with the diagram what are the blocks here. Group 1 and 2 are S block elements. Group 3 to 8 are all P block, and this whole series indicates the transition elements or D block. You can call it as transition metals, transition elements, D block elements, D transition series, whatever you call it. So that's how they have categorized them into different blocks. Okay, now we have clearly seen what are the blocks in the periodic table. Now let's move on. Periodic properties. What kind of the properties exist in the elements in the periodic table? Why do we call it as a periodic table, by the way? Do you know that? Periodic table?
Possibly. Maybe.
No? Periodic comes from the word periodicity. And what is this periodicity? What is periodicity?
Not sure.
Periodicity means repetition. Isn't it so?
Yeah.
repetition of something which occurs repeatedly. So periodicity means something is occurring periodically. And what are those things here in chemistry? Those are the chemical properties of the elements. That includes their chemical properties in terms of chemical reactions. It includes ionization energies. It can include atomic size. It can also include electron affinity and all these properties. So these chemical properties are basically repeated. Chemical properties are repeated periodically in the periodic table. Like you know that all the elements group 1 are called alkali metals. Is it so?
Yeah.
Why they are called alkali metals? Because as you move from left to right, their properties are matching with the same group 1, and all those are called alkali metals. They have similar chemical properties. So that's why we call it as a periodic table. So we have to study here the regular repeating properties of the elements occurring in the periodic table, and we will go through the atomic radii, melting boiling point temperatures, first ionization energies, etc. Okay, now starting from the atomic radii. What is atomic radii?
The distance from the center, the distance from the nucleus to the outer electron.
Okay, radii means radius, and radius of an atom means it is the distance from the center of the nucleus to the outermost shell. You will say shell, outermost shell, not the center of the electron. So in this case we can find out the atomic radii of the atoms by considering the covalent bond. Like you know that most of the elements in the periodic table are basically of the p block elements. They are in majority p block elements, right? On the right side,
Yeah.
most of the elements on the right side are p block elements, and within the p block elements there are cases when the elements are showing the covalent bond formation. This A type represents the type of the atoms which are covalently bonded with each other, and B type represents the elements which are showing metallic bonding. Here you find metallic bonding, and in A type you see the covalent bonding. In the covalent bonding, you know that the orbitals are basically overlapped with each other. They are overlapping. That's why there is a sharing of the electrons in case of the covalent bonding. Because of this overlapping, we should now determine the radius. The radius of such kind of the bond can be determined by taking a half of the distance between these two nucleus. If you take half of the distance between these two nucleus, you can find the atomic radius, because the half of this distance will give you the atomic radius. Are you getting my point?
Yeah.
In these type of the non-metals, the atom, for example chlorine, they do not exist in the single atom form. They do not exist like this. Instead they occur always in the diatomic molecule. Is it so?
Yeah.
So we cannot basically have a single separate atoms. Instead we have a diatomic molecule, and this is a kind of diatomic molecule here of a single element. Let's suppose it is a molecule of the chlorine. We cannot say that the distance from nucleus to the outermost shell will be same in all sides. Like you can see, it is this much distance on this side and it is same on this side, but it is not the same when you try to find here, because it is moving up to the nucleus of the second atom. So for this purpose, we basically consider a half of the distance between the two atoms. That will give you the actual radius of the atom. So that's how we find the atomic radius of an atom. And you should also know that the electrons do not have a clear, distinct outer boundaries. They are not distinct boundaries for the shells, because electrons are always present in the cloud form. Are you familiar with the cloud structure of the atom?
Yeah.
It is here in this book. This is the cloud structure of the atom. Can you see any distinct outer line of the shell?
Not necessarily. No.
No. That's why we cannot say that up to which point should we measure, up to this point or where. We do not know. So that's the reason we basically consider the nucleus of the other atom, which has a clear defined area. The nucleus has a very clear defined area. That's why we can easily calculate the distance between the two nuclei. Is it clear?
Yeah.
Okay, so the left side was for the covalent bond, whereas on the right side we have a metallic type of the element, metal atom. You know that about the metal atoms, the atoms are not overlapping on each other. Instead, their outer boundaries are touching each other from the outside. You know about the metallic structure, there is a array of positive ions and they are surrounded by a sea of electrons. Is it so?
Yeah.
So that's what shown here. It is a metallic bond structure. So for this purpose, we just simply take a half of, again we take the half of the distance between the two nuclei of the metal atoms. That will give you the atomic radius. That's how we calculate the atomic radius of all types of the atom. Just take the half of the distance between the two covalently bonded atoms or two metallically bonded atoms. Is it clear?
Yep.
All right, now you have to tell me the trend of the atomic radius down the group and across the period. What do you expect? What shall be the trend of the radii?
Increase down the group.
Very good.
To be about the same or slightly less across the period.
Slightly less across the period means what? Like it will be decreasing or increasing? Decreasing. Very good. Why is it so?
Because it's more electrons, more protons, more attraction.
Very good. Very good. There are more protons and more electrons, so that will create attraction, stronger attraction between them, and as a result, the valence shell will be drawn closer to the nucleus. So yes, the atomic radius or the atomic size will decrease. So here they have given the graph of the period 2 and period 3 elements, and you can clearly see that as we move from left to right, this is the left element and this is the extreme rightmost element. When move from left to right, the size is decreasing. So that's a decreasing order. And when you come back to the first group again, like you know that this is the element of the first group, lithium, and sodium is also the element of the first group. What do you see the change between these elements? Increasing, yes. So when you finish the second period and come back to the first group of second period, the size will increase. So that's a trend across the period and down the group. Now after this, melting and boiling temperatures. So these elements basically can exhibit their particular melting and boiling temperature, and that depends upon the type of the structure shown by them. The type of the structure: lithium, sodium, beryllium, magnesium, and aluminium. All these elements are basically metals. They are metals. So the type of the bonding shown by them will be metallic. And as you know, the metallic bonding is very strong. So that's why their melting temperature and boiling temperature is considerably high. Their melting and boiling temperatures are higher. But what is exactly the trend across the period and down the group, you have to take into account some other factors as well. So if we move from left to right, by moving from left to right, the metallic bonding is increasing. Do you know why? Metallic bonding is increasing from left to right across a period. Do you know why?
More electrons, more protons.
More electrons and more protons. Basically, you are considering the attraction.
There's more attraction between molecules.
There are no molecules in the metals.
Stronger forces of attraction between the positive and negative ions.
Yes, very good. If you compare sodium versus aluminium, then sodium will release only one electron in its shell, in its surrounding. However, the aluminum will release 3 electrons per atom. So there will be greater number of the electrons in case of the aluminium. And yes, at the same time, there will be greater nuclear charge in the nucleus as well. So that's greater attraction between the positive charges and the sea of electrons or delocalized electron. There will be stronger metallic bonding, and as a result of this stronger metallic bonding, the melting point and the boiling point are increasing from left to right. All right.
Yeah.
I don't know why they have not given the explanations and details of melting and boiling point. They have just shown a whole data in the tabular form and not discussed it separately. I have this all in my Cambridge notes, so I will show you my notes as well if you require. You have just seen there is some explanation down here. You may have noticed that the elements with giant lattice structures have high melting and boiling temperature, and those with simple molecular structure have low melting and boiling temperature. We will explain the reason for this in topic 3. Okay, so you will study the reason in topic 3 of chemical bonding. Chemical bonding will reflect these values. So we can skip this over here and move on to the next topic, which is based on the first ionization energies. So we have just seen that ionization energy increases from left to right. That's what we studied before. Now there comes the anomalies here, which I told you before, that although the ionization energy increases while moving from left to right, but specifically speaking, then there are some exceptions at some particular points. So you can clearly see here the ionization energy is decreasing from this point to this, and this is group number 2 and this is group number 3, and then it again decreases from group number 5A to 6A. Do you know the reasons of this decrease in the ionization energies?
Not sure.
Not sure. Okay, we'll discuss these reasons in our next class because it will take a lot of time to discuss.
Orbit.